Hi, my name is Christopher Caron, and I am a senior undergraduate majoring in electrical engineering and physics at UMass Amherst. Today I'll be presenting my honors thesis on the construction of a Wilson cloud chamber with embedded real-time particle detection and analysis. This project was done for the UMass Electrical and Computer Engineering Honors Departmental track under the oversight of my primary chair, Professor David Kawall, from the UMass Physics Department. So to start off, I'd like to give some background on the project. Of course, this project has to do with particle physics, which studies the behaviors of subatomic particles, and to do that, we need particle detectors. So one of the first particle detectors used to study particle physics was the cloud chamber, and it was used to discover particles like the positron and the muon. In fact, on the right, you can see a picture from the original paper from 1932, which shows a positron passing through a cloud chamber. And you can actually see in this cloud chamber there's a plate of lead, and as the positron passes through the lead, it's slowed down, which changes the radius of its curvature. And from that, we can determine which way it's traveling. And then now that we know which way it's traveling, and we can look at the direction of the curvature, we can determine that it must be a positively charged particle of a mass comparable to the electron. And that is actually exactly how we discovered that the positron exists and that there is an antimatter counterpart to the electron. To build a cloud chamber is actually very simple in theory. We need to create a sealed chamber with a temperature gradient. At the top we have warm alcohol, and at the bottom we have a very cold metal plate. So the alcohol vapor is going to fall through the chamber and condense into a cloud above the floor plate. When particles from the atmosphere pass through the cloud, they knock electrons off of the molecules in this cloud, which leaves behind a trail of ions. Then the mist will nucleate around these trails, and we end up with dense visible lines like you see in the picture to the right. So in this project, we're trying to study these lines, and I've included some images here to the left, which are from the Nulido Cloud Chamber's website. And you can see the interesting thing is that each type of particle that we can detect actually leaves behind slightly different looking tracks. Some of these tracks are actually quite rare, and so generally you need to be constantly watching a cloud chamber or recording videos to see what you get. And there are plenty of videos on YouTube to show this happening. Here's one from the Nulido channel that I want to show. And this gives you a really good view of what the tracks look like inside a chamber. This is a slow motion video, so you can see there's some very dense tracks that form and then slowly fade away. And then there are some thinner tracks too. And these are different types of particles that are being detected. This is exactly what we want to see in our project. In this project, our main goal is to construct, from scratch, a high-quality cloud chamber detector that we can adapt for a public exhibit here on campus. And one of the biggest challenges is that, unlike most chambers you'll find on YouTube, we'd like ours to be a large volume chamber that can sustain itself for long periods of time. A common technique is to cool chambers using dry ice, so obviously we can't do that here, and that makes things a lot more challenging. And then because this is an engineering thesis, we'd like to be able to automate data collection and remove the need for long videos or the constant attention of a researcher. So we want to use computer vision to have an embedded computer detect the tracks and log them in a database for future analysis. And this could be useful if we wanted to run the machine for many days at a time and count up everything that happens. We'd also like to record things like the length of the tracks, which can give us hints about the energies of the particles in the chamber. To date, we've actually built two separate cloud chambers. The first was during the fall semester, and it was really just a large acrylic box. At the roof we hung a 3D printed trough full of warm alcohol, and at the bottom we had a metal plate that was actually cooled with dry ice. We had an Arduino reading off the temperatures of the alcohol and the floor plate, and also controlling a strip of LEDs. And really the only purpose of this chamber was to give us some information about what conditions make the best tracks, and also give us some real videos of tracks that we could begin to analyze. Now, in spring 2021, we've moved on to a refined version, and this version has a refrigeration unit instead of dry ice so that it can run for much longer. We're also planning on pumping warm alcohol up through the chamber to control the amount of vapor in the chamber at any given time, and we've begun programming an NVIDIA Jetson Nano for image processing, which I'll discuss later. So here on the left you can see an image of our refrigeration unit, which is capable of sustaining temperatures around minus 60 degrees Celsius. And one thing you'll notice is that it comes with this odd coil, which is not so easy to connect to a large flat floor plate. So on the right is one of our custom components, which we've designed and had machined, and this accepts the coil and is filled with isopropyl alcohol, which has a freezing point of about minus 85 degrees Celsius. And the idea is that the liquid alcohol will facilitate thermal conductivity between the cooling block and the coil itself. And then we take this cooling block, which you can see again on the left, and we stick it to the bottom of an aluminum plate, which is on the right. And now you can see we have the floor of our chamber. Right now we have this temporary glass box, which will soon be replaced by a much cleaner looking glass box assembly, but the basic idea is all there. And this is how far we've gotten this semester. You can see we just have an orange cup inside to hold our liquid alcohol, so that will soon be replaced also, but we've turned on the cooling unit and shown that we can achieve floor temperatures cold enough to facilitate the formation of these tracks. So on the left here you can see our revised chamber with all the lights on, and on the right you can see what it would look like during operation. As I mentioned, we're using a Jetson Nano to perform our image processing with a Raspberry Pi 2 camera. And we made this choice because the board is becoming very popular. It has a lot of support for training neural networks, which is something we'd like to investigate someday later, but for now it's also really well suited for running OpenCV and Python. The general idea is that we take our camera feed, we do some background subtraction, then a series of algorithms such as blurring, dilating, and canny edge detection to prepare the image for a Hoff-line transform. And this is an algorithm that is actually built into OpenCV, and it returns the endpoints for as many line segments as it can detect in the image, basically fitting line segments to the tracks in frame if there are any. And then if we pass a certain threshold, we can identify that frame as worthy of recording and take a picture. And this doesn't need to happen too fast because, as you've seen, the tracks can persist for a couple seconds, so even with a modest frame rate, we can get a good record of what's happening in the chamber. So now I want to share a couple results from last semester. Getting these tracks in the prototype chamber was in practice not very easy to do because a lot of time had to go into tweaking the system and then recording footage. But of course it paid off because in the end you can see we definitely have some tracks. And the hope is that with a more robust setup and less air drafts and more uniform vapor density, we can get much denser and thinner tracks, which will make the image processing algorithms perform even better. So as you watch, you can see a couple tracks form. I think there's some on the right, some in the corner. We'll keep watching here. There's a really thick one. And then here's a good video of one on the left. So far things are looking good. So another part of this project that I haven't mentioned yet is actually simulating these tracks on the computer to practice with while we're busy building our chamber. And so I use processing, which is a Java-based language in IDE that's really great for creating images. And on the top left, you can see my simulated track with a bunch of noise all around it. And then you can see some more code I wrote with OpenCV filtering and extracting that line from the image. And then in the bottom left, you can see I perform a Hoff transform, and I detect several lines, and then I combine these in the bottom right picture into one best guess line, which represents the entire track. And you can see this works really well for still images. On the right, we have a picture of a track that we actually took last semester and processed, and that demonstrates how we can get really nice crisp lines even on the prototype chamber, which is really promising. So at this point I'd like to interrupt and show off some of the code that we have running so far. So over here you can see some OpenCV code that I've written, and this is going to look at pre-recorded video from last semester. And if I move this to the side and press play, on the left you're going to see the original video, and then on the right you're going to see the output of the algorithm. And what's happening right here is every time a track is detected, it's getting highlighted, and then these green lines are the output of that Hoff transform that I mentioned. And right now all of the frames that have lines in them are actually getting detected and saved to this folder over here. So the next big task is going to be to implement some clustering algorithms, and we're going to be looking at factors such as line slope and location, and maybe the time it was detected, and try and cluster these lines so that we can group them into single tracks as opposed to big groups of lines like you see here in some of these images, for example. So what's left to do right now is really finish the refined prototype. We want to build that alcohol delivery system so that we can get lots of vapor, and we want to make some general improvements to the construction of the chamber. And then we also want to convert that OpenCV code, which works really well for still images, into code that is constantly being performed on a live video feed. We're very confident that this is realistic for the last month or so of the semester, and what we hope to leave behind is a robust setup that can be easily adapted into a display and installed into the physics building here on campus as an exhibit to show off particle physics and demonstrate the tracks that the system detects. And also in the future, I'd like to leave the door open for maybe training a neural network to distinguish between different types of particles in the chamber, or other more advanced algorithms that we may not have time to get to this semester. Here's a list of sources. Feel free to pause here and check them out. These citations will be included on the final thesis document that I'm writing, and they've helped quite a bit along the way. And otherwise, that's all I've prepared for today, so thank you for taking the time to come check out my project, and have a great day.